All right, so in this video, we're going to be looking at the periodic trends. Now, the periodic trends are pretty complicated. I would be really surprised if I don't get a couple emails and a couple Google Meets about, looking for some further clarification. So, as we start to get more into this, more advanced chemistry, please reach out, okay? If you have questions, please talk to me, all right? Let me help you work your way through it, okay? But let's jump right in. So I'm going to make myself just a little bit smaller there. I'll have to move around today. But when we're talking about the periodic trends, okay, we're studying something that's called periodicity, right? And you've probably heard someone say before, like, how often do you go to the beach? Oh, well, periodically, right? So periodicity, doing something periodically means on a, semi-repeating schedule, right? It happens every now and then. And in the middle to late 1800s, a lot of chemists were studying something we call periodicity. They had noticed that there was this, curious repetition that seemed to occur in the elements when you organize them a certain way. So if you organize them by their atomic weight and you put them into a chart, then you could, depending on where you broke the chart, you could make, elements that were in the same family, right, in the same column. You could line them up in such a way as they had similar characteristics, which they thought was peculiar. Now, a lot of scientists did this. They put these tiles, they called them tiles, they were like the little pictures of the element, into these charts. But the guy that gets credit for creating what we now call the periodic table, he did the exact same thing all these other people did. All right, he organized them by atomic weight. He broke them, broke the end of the row so that the next row they would have family groups. But he didn't assume that every element had been discovered. So Dmitry Mendeleev is credited with the creation of the periodic table. There were 58 known elements at the time. He put them in order, and instead of just, the next one goes here, the next one goes here, if the next one didn't fit a pattern, he skipped it. So this is what I mean. Let's say we've got a couple of these different element tiles, right? So we're going to put them out here. And then we're looking at our next row. And the problem is, we'll say this is solid red. This has a line. This has a line. This has that line. Okay. Well, when he breaks it, there's the first one. Here is the second one. And he's going, okay, if we look down the group, we've got matching trends. They're starting to behave the same. But the problem is the next tile he's got looks like this. And so most scientists, they stuck it right here. And this is what made Mendeleev pretty much the best. So let me grab my eraser. All right. He left that spot blank. And he said, no, I'm going to put it right here. And he said, whatever goes in this box, it hasn't been discovered yet. And this is why Mendeleev gets the credit, okay? And so he actually started to make predictions about these question marks he left. One of the first one that he predicted was gallium. Gallium is right underneath aluminum on the periodic table. So you have aluminum right here. And gallium is the next element down. Now, at the time, gallium hadn't been discovered when Mendeleev did his periodic table. And so underneath aluminum, he put a little question mark. He called it Eka aluminum, which I believe comes from Sanskrit. Don't ask me why I remember that, but because I don't know why I remember that. But he started to make predictions about it. He said it's going to be a metal. He said, it's going to be silver. It's going to have some luster, right? He said it's going to be kind of a semi-metal, so it's going to have a really low melting point. And he made all these predictions about it. He even went so far as to calculate the density. When they actually discovered gallium, he was right about like everything. Gallium is a really cool metal. If we ever end up back in the classroom from this, virtual environment, I'll show you some. It is a metal at room temperature, solid, silver, and if you hold it in your hand, it will melt and turn into a silver puddle. It is a really low melting point. It's pretty cool. He also predicted things about scandium and germanium, and this is why Dmitry Mendeleev is credited with the initial periodic table. But doing it by increasing atomic mass turned out to be the wrong way to do things, okay? Because if you look on our periodic table today, you can actually find a couple instances where the mass is reversed. It doesn't go higher as you go to the right. It actually has some flip-flops in there. And so the guy that figured out the right way to do it, was Henry Moseley. Henry Moseley is an English scientist, and instead of organizing things by increasing atomic mass, he organized them by increasing atomic number. And that gets us to the modern periodic table. The modern periodic table follows the periodic law. It says that the physical and chemical properties of the elements are periodic functions of their atomic numbers. So by saying it's a function of their atomic number, what that means is you have to organize them by atomic numbers in order to see those repeating patterns, that periodicity. Okay, so that gets us to the periodic table as we understand it today. Now, the periodic table is pretty cool. It is, in my opinion, one of the greatest achievements of mankind, because think about it, every single thing in the known universe is made from those 118 elements that are on that table. And we've discovered so far all of the ones that we know about. We've made some of our own elements, right? There are some synthetic elements that we make in mass accelerators and cyclotrons. And we have organized them in such a way that it's easily accessible. I mean, think about that. You're in high school, and all of the known elements are available to you on a piece of paper that is pretty easy to reference. That's an incredible achievement. Now, when you look at the periodic table, and you'll get used to drawing this thing, sketching it out, you'll notice that it's organized into some sections, all right? And the sections look something like this. Hopefully this doesn't look too bad. All right. When you look up and down a group, all right, this is looking up and down a column, rather, we call those groups. Those are families, okay, and that should make you think of common characteristics, all right? I know we've already talked about the alkali metals, the alkali earth metals, right? Alkali metals are group 1, alkali earth metals are group 2, the noble gases are group 18, the halogens are group 17, the chalcogens are group 16, going up and down in those columns. And the horizontal rows, going left to right, are called periods. There are 7 periods. 1, 2, 3, 4, 5, 6, 7. They go straight across. The elements are then broken into these blocks. So this first 2 rows, the first 2 groups is called the S block. We have the D block, which is the transition elements. We have the P block, and then we have the F block, okay? So the periodic table is organized further, all right, using those systems. Now, here's what we want to do with this material, all right? So nice little review with the periodic table, a little bit of new information. Now we want to move into these trends. We want to talk about these, periodically repeating patterns. And there's 2 things that we want to do with this, all right? Number 1, you got to keep in mind that atoms are physical entities. They are real things. They're too small to really see, but they're there. We can, all of our data supports their existence. And their behavior then, because they're a real thing, is related to their structure. So just like if I want to, put some drywall up, all right, the drywall has to be suspended from the 2x4 backing in my wall with a screw. Or I guess I could use a nail, but a screw is a better structure for that. So when I think about a screw, the structure of the screw is related to its function. So a screw is actually a simple machine. It's just an inclined plane that goes around and around and around a point. Like so. So there's my screw. And if I turn the screw to the right, all right, assuming the regular threads on the screw, it goes into my drywall, and eventually it penetrates the 2x4 wall behind it, the studs, and it will hold my drywall up on the wall. Atoms have structures, and those structures, carry a behavior with them. They have a function. So keep that in mind. The structure of the atom, how it's put together, is going to help you explain the trends themselves. The second thing is that we want to understand the trends kind of in light of their structure that underpin each trend, because that's going to help us understand that atom itself and the behavior of the atom. And I'll give you some examples for that as we go on. So let's talk about this key structure, the inner electrons. So you can see down here on the left, we have some Bohr models of the atom. Right? I know they're Bohr models because I see that the electrons are moving in circular orbits. We know that's not, how they really move, but it's a great model for our conversation. Now, lots of times people just teach about, or you learn about the valence electrons in biology. We're going to talk about valence electrons in chemistry a lot, and the inner electrons kind of get ignored. So you can see here that boron has 3 outer electrons, but it also has these 2 inner electrons. All right. Silicon has 1, 2, 3, 4 outer electrons, but then it has 10 inner electrons. Okay. And, antimony, Sb is antimony. It's got 5 valence electrons, and it's got 46 inner electrons. So a lot of times people ignore these inner electrons because they're not involved in bonding for the most part, but they're really important for explaining the interactions between the valence electrons and the nucleus. Because remember, the nucleus is a positively charged space. The electrons are negatively charged. So the behavior of a valence electron is influenced by the inner electrons that interfere with the pull from the positive nucleus on the valence electrons. So think about it like this. I have a positively charged nucleus. If this is my first valence electron, there's nothing in between the 2 of them. All right, there is a very strong force of attraction there. On the other hand, if I have a positively charged nucleus, and then I have a bunch of inner electrons, right? A bunch of inner electrons. And then way out here is my valence electron. Well, this guy is a little bit more free. Okay, he's a little bit more free from the pull of the nucleus because there's all these other electrons that the pull kind of has to fight through in order to get to it. So we call that the effective nuclear charge of an atom. It's the measure of how much influence, how effective the nucleus is at interacting with those valence electrons. It directly depends on the inner electrons. So the more inner electrons you have, the lower the effective nuclear charge. So we'll write that down. More inner electrons equals lower effective nuclear charge, ENC, all right? ENC, effective nuclear charge. An effective nuclear charge is actually a really important way that we describe a lot of these trends, all right? So let's look at some of those. Here are the trends. We have electron shielding, effective nuclear charge, which we just talked about. We're going to talk about atomic and ionic radii. We're going to look at metallic character, the energies of ionization, electron affinity, and electronegativity. Now, I'm just going to give you a heads up. This one, really important. This one, really important. These would be my top 4, okay? Moving on. Let's look at the first one, electron shielding. So we just kind of talked about that. If you have the nucleus, right, which has some number of protons, the atomic number is Z, right, so that's what that means, there's some number of protons. It attracts the outer electrons to it because the outer electrons are negative and the nucleus is positive, okay? The problem is all of these inner electrons are also negative, and so they force the outer electrons away. They repel them. The more sub-level electrons or inner electrons that you have, the less of a net attraction the nucleus has on the outer electrons. They get in the way, okay? That's called electron shielding. When the electrons in this layer right here, the sub-level electrons, so this would be the sub-level. It's below the valence level. You can only have one valence shell. You can have many sub-levels, all right, or subshells. You can have many of them, as many as there are, okay, up to 6. There we go. Now, here's how the trend works, right? Because we said if we look at the periodic table, there is a trend. Well, going from left to right, the electron shielding remains constant. You're not gaining any new sublevels. And here's how I know how many sublevels I have. So these are the energy levels. 1, 2, 3, 4, 5, 6, 7. There are 7 energy levels, okay? Therefore, there are 7 total levels of electrons. Well, if you're in row 1, if you're in period 1, you don't have any sublevel electrons. If I want to draw a hydrogen atom, it's got 1 proton, it's got 1 electron, and here's my Bohr model. There is no sublevel electron. There's nothing below it. But if I want to draw lithium, lithium has 2 electrons in the first sublevel, right? Here's the first one. Here's the second one. Lithium has a 3rd electron. It's further away from the nucleus. It also has 3 protons. See, my pen will catch up. There we go. Oh, that was supposed to be around. There we go. So there are 3 protons. Now, this inner level right here is my sub-level. I have 1 sub-level because I'm in group 2. All right, let me throw these back up there. 1, 2, 3, 4, 5, 6, 7. Okay? Now, as I go down a column, all right, I go down a group, then the shielding is going to increase. And that makes sense. Let's say I compare potassium to sodium. So here's sodium, Na. It is in the 3rd energy level. And so if I look at, here is, let's say, the nucleus. Well, it's got the 1st energy level, the 2nd energy level, and its valence electron is in the 3rd energy level. So there are 2 sublevels in between sodium's valence electron and the nucleus. But if I look at potassium, well, potassium has 1, 2, 3, and its valence electron is in the 4th level. So here I only have 2 sublevels. Here I have 3 sublevels. So as I go down a group, all right, my shielding is going to increase. There are more electrons in the atom, and that should make sense to us, right? I mean, think about gold. Gold, right, Au is number 79. That means it's got, as a neutral atom, 79 electrons. Well, you can only put, 2 in an orbital. You can only put, at most, 8 in a sublevel. And so, you've got all of these other levels above it that are going to be filled in, interfering with the nucleus's pull on the valence. So that's electron shielding. Now, effective nuclear charge and electron shielding go together. So the exact force felt by the valence electrons is really easy to find. You do the number of protons minus the number of inner electrons, and that gives you the E and C. We often abbreviate that ZEFF, the effective number of protons, right? The effective nuclear charge. Now, I'm not going to ask you guys to really calculate that or anything, but I want you to know that's how you find it. So let's just do one. Let's do the ZEFF for hydrogen. So hydrogen has 1 proton. It has 0 inner electrons. Therefore, the ZEFF equals 1. Pretty simple. Let's look at potassium, right? K. So let's go back to our periodic table. K is number 19. So K is number 19. So 19 minus, all right, I need to do inner electrons. Well, I know I've got 1 valence, okay, because I'm in group 1. I have 1 valence electron. Also, if you're looking for valence electrons, this group has 1, this group has 2, 3, 4, 5, 6, 7, and the noble gases have 8, with the exception of helium, who's happy with 2. Don't worry about helium. These guys all have 8. See how you can count that from the left? 1, 2, 3, 4, 5, 6, 7, 8. You skip these guys. You can't count them. They are the transition elements and transition metals, and they're called that because they have varying number of valence electrons. It just kind of depends. They can have multiple different charges. So anyway, potassium has 1 valence electron. It has 19 total electrons, which means it must have 18 electrons in the middle. So 1 minus 18 equals an effective nuclear charge of 1. There we go. Now, this is a pretty cool graph. This compares the effective nuclear charge, okay, of an atom to its actual atomic number. So if Z was equal to Z effective, it would follow this dotted line right here. We can see that it doesn't do that, all right? Instead, we get these little bumps. So it goes up and it comes down. It goes up and it comes down. You could probably predict that the next one is going to go down here and the next group will keep on going over. So this is what we mean when we talk about periodic trends, okay? Here's the other thing, right? It says, what does the data reveal about effective charge as you progress through the elements? Well, what's the effective charge doing? It's slowly but surely, right? If we drew a line of best fit, it's increasing. So that's you know, kind of obvious, right? Effective nuclear charge increases as you go up and to the right, okay? So helium is going to have the highest value, right? It has no valence the valence electrons have no shielding from either of the protons, all right? Up and to the right. So that means if I'm going right on a period, it's increasing. If I'm going up in a group, it's increasing. It increases up and to the right. Next trend is atomic radii. Remember, while you're watching this, if you need to take a break, okay? Atomic radii. Atomic radii is pretty simple. It's half the distance between the nuclei of 2 identically bonded elements. So here we have, let's see, covalent radius is 133 picometers. It could be maybe nitrogen, maybe hydrogen, I'm not sure. In this example, we have 2 atoms. They're obviously the same atom because they're both purple, and you know, that means they're the same thing. And if we look at the distance from there to there, right, and we cut it in half, right, that gives me the radius that should be the size, right, of that circle. So scientists can't see the nucleus, okay? We can see the outside. We've seen all the way down into the level of the outermost electrons, but we haven't ever seen the nucleus. So since we can't see the nucleus because the electron clouds are in the way, you have to, you know, kind of work around the mountain. You can't go through the mountain, right? So to figure it out. So we find the internuclear distance and we just divide it by 2. Now atomic radii trends down and to the left. Francium is the largest atom. Helium is the smallest atom. Now, this is affected by 2 things. It's affected by the number of energy levels, the number of sublevels, right? More sublevels means you have to be getting bigger. It's also affected by the effective nuclear charge. If the nucleus is pulling on the valence electrons really strong, well, it contracts. It pulls the atom in closer. So see, understanding electron shielding, the sublevels, and understanding effective nuclear charge lets us explain the trend in atomic radii. So I can look at this and I can make a lot of judgments about those other 2 trends just knowing this about atomic radii. I can say helium must have a really strong effective nuclear charge. It must have really weak electron shielding because nothing is stopping those nucleus protons from pulling the valence electrons in really tight, making a small atom. On the other hand, I can look at francium and say francium must have a lot of sublevels. Electron shielding must be really high, and the effective nuclear charge must be really low because the nucleus is not doing a good job of like pulling the valence in. In fact, it's getting stretched. And so the atomic radii is directly linked to our understanding of effective nuclear charge and electron shielding. So this is what this slide says. The structure and behavior conversation that I just talked about with that graph is what we want to be able to do. We want to be able to connect our trends. So if we look at electron shielding and effective nuclear charge and their influence on atomic radii, here are the 3 bullet points that you want to know. The more shielding, greater electron shielding is caused by more energy levels that increases the distance from the nucleus to the valence electron. So if I'm increasing the distance, well, then I'm getting bigger. The lower the effective nuclear charge, the less influence the nucleus can, exert on the valence electrons. That lets those outer electrons move really freely. That's going to be important in a minute. The low ENC goes with a larger radii. So I have low effective nuclear charge. It's not very effective holding in those valence electrons. My atom gets bigger. High effective nuclear charge, the nucleus is really strong. It pulls everything in. So it's associated with a smaller radii. Now look at this data, okay? What can we interpret, okay, just looking at this data? So let's look at what we got here. First of all, I don't know if you've ever seen it before. This is a 3-dimensional bar graph. It's got 3 rows moving back. And this is our row number, our energy level. So 1, 2, and 3. Here's the covalent radius, okay? And here is our group number. So this is like row 1, group 4, row 1, group 5, row 1, group 6, so on and so on. Okay, so what do you notice, right? If I had to draw a line of best fit, it'd have to be a 3-dimensional line, but it would definitely be going that way. Okay, it'd be going, that was really terrible. Let's see here. There's a little there. It's going back. Okay, so what we can tell is that the bond length is influenced by the atomic radii. The larger the atom's radii is in the first place, the longer we expect the bond length to be. So, I mean, that should make sense, right? If you put 2 ginormous tires next to each other, well, there's a long way between their 2 midpoints. If I put 2 little baby tires next to each other, they're really close together, all right? That means that bond length, right, the distance between the 2 nuclei is influenced by effective nuclear charge and shielding, because shielding and effective nuclear charge mess with the atomic radii, and the atomic radii in turn messes with the bond length. And I know this is a bond length because it says covalent. Covalent means that there's a bond that's occurring. We talked about atomic radii. Let's look at ionic radii. So the ion is the thing in this color right here. Okay. The other color is the normal size as the atom. So we can see that this metal, it's getting smaller, right? The metals are getting smaller. The ion is smaller than the atom. The atom is here on the outside, so it got smaller. On the other hand, our nonmetals have gotten bigger. Well, does that make sense? Well, let's see. Metals form cations, right? They form positive charges, which means they lost their outer electrons. So here's my valence electron. Here's my subshells. I lost my outer layer. Well, now my outermost sublevel is the new valence layer. It got smaller because I lost those outer electrons. On the other hand, my nonmetals are gaining electrons. Electrons repel each other, so they try to get further away. So as I put more electrons in there, they're like, move away from me, and they expand a little bit. Now, ionic radii always increases down a group, always. It's kind of variable across the row. So we can go back and we look at that. Yeah, if I look down a group, the ions are definitely getting bigger. However, if I look like across here, I'll notice that that's definitely bigger than this. And, this one looks like it's increasing, but, from here to here. But if I look here to there, it looks like it's decreasing. So it's variable across the row. But you can always count on it to go to increase as you go down a group. Structure and function. How do we explain it? Well, it's shielding and sublevel electrons again. Okay, the metals are giving off their valence electrons. That means, so let me draw that for you. So here's lithium. It's got 3 protons in the nucleus, and normally it has one set of valence electrons, inner electrons, and it's got one valence electron. So that's lithium. All right, let me switch my pen color here. Okay, so lithium, when it's +1, that means it lost an electron. It didn't lose a proton, it just lost one of its electrons. So here, I have no sublevels. All right, none. No sublevels. Over here, I have one sublevel. Can't spell. Sublevel. There we go. So obviously, this is attracted in, right? There's a force of attraction there, so this is smaller. And so I can again explain that with shielding and sublevels. When I give off a valence level, there's now one less sublevel electron that's doing the shielding. So the effective nuclear charge is going up, the shielding is going down, the atom gets smaller. Okay? Next trend, metallic character. This is one of my favorite pictures. It's heavy metal, right? Rock and roll. We have lead and zinc. I used to have a coffee cup with that on it, but it fell apart. Sad times. Anyway, some characteristics of metals, right? We already know these. They're malleable. They're ductile. They can conduct heat and electricity well. They'll form cations when they become ions. They can form alloys that can bond 2 metals together. And they operate under that sea of electrons model, right? When they're bonded together, the electrons just kind of run wild. Well, metallic character increases down and to the left. Okay, you probably know, if you've been paying attention, that everything kind of centers around this staircase when it comes to metals and nonmetals. So if you're to the right of the staircase, you're probably a nonmetal, unless you're one of these guys, in which case you are a semi-metal. Okay, and if you're on the left, these guys are semi-metals. Okay, so everybody to the right of that line is a nonmetal. Everybody to the left is a metal. But we're talking about the most metal. Well, francium is the most metallic element because it increases, the metallic character increases down to the right. What does that mean? As you go down a group or to the right, you will find that they are more malleable, more ductile, better conductors of heat, better conductors of electricity, right? They are better at being a metal. They have those characteristics. Well, how do we explain that? Well, it's pretty simple. Francium has one valence electron. It's got 6 sublevels of electron shielding it from the nucleus. That outermost electron is given off almost immediately. That makes it a cation. There it starts to behave like a metal, right? There's not a lot of like overthinking here. This is not rocket science. If you look at helium doesn't have any shielding, holds on to its electrons. The nucleus, well, let's look at fluorine, not helium, because helium's stable. Fluorine has 7 valence electrons. It really, really, really wants 8. It's got a pretty strong effective nuclear charge, so it's pulling electrons in. It's not going to give them up. It's not going to allow that sea of electrons to occur, so it's not going to conduct electricity. It's brittle. It's rigid. It's not like a metal at all. The next trend, energy of ionization. All right, so this one, the other ones are a little bit easier to understand. Energy of ionization can be tough, so let's take our time with it. It's the quantity of energy that an atom in the gas phase, so that's what gaseous means, in the ground state, so that means it's neutral, must absorb to discharge an electron and make a cation. So that's the official definition. In other words, it's the energy needed to remove one electron. That would be the first energy of ionization. The second energy of ionization would be how much energy it takes to remove the second electron. The third energy of ionization would be how much energy it takes to remove the third electron. The lower the energy, the easier it is to remove an electron. Well, that makes pretty good sense. The higher the energy, the more difficult it is to remove an electron, and so the less likely the element is to be metallic. Now, usually we express this energy in kilojoules per mole. A joule is a SI unit of energy. Kilojoules is thousands of joules. And that's going to be the amount of energy it takes for all the atoms in a mole of the element to lose one electron each. The energy of ionization, when we graph it, has a very similar looking graph to that effective nuclear charge graph, right? We can see peaks and valleys at regular intervals. And when we look at this, we ask ourselves a couple questions, right? Which elements have the highest energy values? Well, at the very top, we have helium, neon, argon, krypton, xenon, and radon. Well, those are the noble gases. So think about it. A noble gas doesn't want to interact with anybody. It has its stable configuration of electrons, right? Usually 8 valence electrons for everybody except helium. It doesn't want to give that up. It's stable. So it makes sense that the highest ionization energies belong to the noble gases. Well, who has the lowest? Well, we look down here, well, lithium, sodium, potassium, all right, rubidium, cesium, all right. These are all the group 1 metals. The group 1 metals are really reactive. It takes hardly any energy to get them to dump an electron. And so what we see in nature, noble gases don't really react. Alkali metals really do react, is backed up by this graph. Can we kind of infer some things about metallic character and energy of ionization from this? Well, yeah, they're opposites. All right, these guys at the bottom, these guys are the most metallic. They also have the lowest energy of ionizations. So most metallic is the lowest energy of ionization. You could also do it the other way, right? The higher the energy of ionization, the less likely they are to be a metal. Now, when we look at energy of ionization, it trends up and to the right. Lower energies belong to the metals. Francium is obviously the lowest because it's the most metallic. Okay, noble gases have really high energy of ionizations, so technically we classify them in the non-metals. The trend line is going to go up and to the right, so that means as you go up a group, it's going to increase. As you go to the right on a periodic table, it's going to increase. Now, electron affinity is often confused with energy of ionization. Don't confuse those. They're two different things. They have two different names. They must mean two different things. So here's the definition. It says the amount of energy released or spent or used up when an electron is added, there's the key, to a neutral atom in the gaseous state to make a negative ion. So remember, energy of ionization is how do you make a cation. Electron affinity is how you make an anion, a negative ion. Okay? Here it is in simple terms. If this value is positive, the element is very unlikely to become an anion. Those are the metals. So remember, metals usually have positive charges. If they have a positive electron affinity, it's probably a metal. It's just a little mental trick. If the value is negative, the element is likely to add an electron. Nonmetals have very low negative values. Okay, so let's look at a graph. Again, we've got stair steps. Let's ask those same questions. What elements have the lowest values? All right, now check out this graph. Negative 400 is at the top, plus 50 is at the bottom. Now, just pause for a minute. Science is an important discipline because it teaches us how to analyze data. You might not grow up and be a chemist, but I guarantee you as an adult, you'll see a graph on television at some point. Something that you should look out for is a graph that shows what somebody wants it to show on purpose, right? I've manipulated this graph by making the y-axis in the vertical direction show negative numbers. So these are actually the lowest values. It's really important that I have an understanding of science so that I know to look at the y-axis and the x-axis. It's also why it's really important that we label the axis, all right? I know I've got the atomic number down here. I've got electron affinity in kilojoules per mole, and my numbers all have their signs, okay? There's negative numbers there. So look at this. What elements have the lowest values? Well, francium, chlorine, bromine, iodine, and acetylene. These are the halogens, okay? Well, why are the halogens really likely to become negative ions? Well, if they gain an electron, they get to act like a noble gas. They're stable. So yeah, that makes sense. They really want to add one. They're very likely to do that. Look at the elements with the highest values. Right? Helium, neon, argon, zinc right there, krypton, xenon. All right, look at mercury. It's off the chart. So they are going to not add an electron. It doesn't mean they're going to be positive. It just means they're not going to add an electron and become negative. So what does a negative value for energy tell us? Well, hopefully you're picking up on the fact that the more negative it is, the more likely they are to add an electron. And notice something. Chlorine is the most, or has the highest electron affinity there, according to this graph. Our trend goes up and to the right, okay? It stops at fluorine. Helium does not have an electron affinity. We have to kind of draw a line here. So let's go back and make sure we understand that. Here are the noble gases down here at the bottom, all right? So we say that the trend line goes up and to the right, but it's going to stop at fluorine. So we say that fluorine is the most electronegative, or sorry, the most electron affinity belongs to fluorine. It's a trend. It's not perfectly true. According to that last graph we looked at, chlorine does, but it's good enough. It's close enough for government work, right? It's close enough. Now, how can we explain electron affinity? Well, nonmetals have greater effective nuclear charges. That makes it easier to attract and add electrons to the valence shell. The shielding remains constant as you move to the right, but the number of protons is going up. That increases the pulling power of the nucleus. So let's make sure we understand that, right? If I look at the periodic table, let's go to this slide, okay? And I say, so just ignore the words on here. We're just looking at the periodic table. These guys are all in group 2. So they all have one sublevel electron, the first row. Fluorine, all right, has, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, right? 1, 2, 3, 4. Yeah, it's got 9 protons. So lithium has 3 protons. Fluorine has 9 protons. Lithium's effective nuclear charge is 1. Fluorine's effective nuclear charge is, we can only count inner electrons, so it's 7, right? That's a huge difference. So fluorine is stronger than lithium. So as I move to the right, the shielding doesn't change, right? I have the same number of inner electrons no matter what, but the number of protons is going up, and so the pulling power increases. Metals have a lower effective nuclear charge, so they struggle to attract any more extra valence electrons, right? Their nucleus isn't strong enough to pull in those extra ones. All right, let's look at electronegativity and the Pauling scale. Now, Linus Pauling is one of my favorite people, okay? I actually have his chemistry book. I have it right here. It's pretty cool. If I ever got to adopt a textbook, this would be the textbook. This is a phenomenal book, okay? It's unlike any textbook you've ever seen. It's written more like a novel, more like a history book than a regular textbook. There's no like vocab or anything like that. It just kind of takes you through chemistry. I really like Linus Pauling. He had a lot of really good ideas. One of his ideas was the Pauling scale of electronegativity. And electronegativity is the measure of the tendency of an atom to attract a bonding pair of electrons. Here's the deal. You can only measure electronegativity in a bond. So look at the noble gases. They don't have any numbers because they don't bond, except for xenon, which will actually bond. So it does have one, okay? Fluorine in the Pauling scale is set at 4. 4 is as high as it gets. And you can see that the trend generally goes up and to the right. Now, what do we mean when we say attract an electron in a bond? Well, here's what we mean. If you have H2, all right, so this is an H, and it's bonded to another H. This is letter A right here, okay? So I have H bonded to H. A bond shares 2 electrons. You can see that electron there and an electron there. Well, hydrogen has a Pauling value of 2.1. So if I have 2.1 here, and I have 2.1 there, the electrons are equally shared in the bond. They spend the same amount of time on both sides. And that means there is no unequal attraction of the electron. The electrons are equally shared. Now, if we look at B, we have atom B is slightly more electronegative than atom A. So the electrons get pulled closer to B. So let's see what that would look like. Let's take hydrogen, which is 2.1, and bond it to fluorine. So this would be hydrofluoric acid, HF. There's my H, there's my F. Well, the electrons are pushed towards fluorine. And so this gives fluorine a partial negative charge. Partial positive charge must be on hydrogen. So the electrons spend more time around fluorine than they do on hydrogen. This is a polar molecule. It has a dipole moment. So if you think back to biology, we have a water molecule. Well, oxygen is more electronegative than hydrogen, okay? We can put a number on it, 3.5 to 2.1. So since it's got a greater polarity, a greater electronegativity, it pulls the electrons towards oxygen. They spend more of their time, up here, gives us a partial negative, and leaves hydrogen with a partial positive. In number C, we have atom B has completely attracted the electron pair. It's all the way over here. It's been donated. This gives us a true negative and a true positive. See, this delta means positive, partial. You don't have any of those over here. This is a true positive and a true negative. So this would be an ionic bond. We have true ions. We have two charges. So this would be something like Na and Cl. I have completely donated over the electron. So here's Pauling. All right, he won the Nobel Prize. He said numbers close to 4 have a high electronegativity. Those will be our nonmetals. Numbers close to 0 have a low electronegativity. Those will be our metals. Notice the graph. It's got that same stair-step kind of look. Same questions, okay? Which elements have the highest electronegativity? All right, well, electronegativity is right there. The atomic number Z is on the bottom. We're looking at 4 from 1, so our y-axis looks normal. And look at the top. Fluorine, chlorine, bromine, iodine, astatine. There are the halogens, okay? They have the highest electronegativity. They're attracting electrons to themselves. Look at the lowest. Lithium, sodium, potassium, rubidium, cesium. All right, our group 1 metals have the lowest electronegativity. They're not attracting electrons in a bond. They're giving them away. So what's that tell us about the trend arrow? Well, it must trend up and to the right, right? There it is. Francium has the lowest. Fluorine has the highest. Again, electronegativity stops at fluorine. It does not progress into the noble gases. And fluorine is the most electronegative element. All right, so that is the periodic trends, okay? When you're looking at this thing, I know that's a lot, okay? I will be absolutely floored if you guys don't have questions. So please reach out and ask questions. I know that's a tremendous amount of material. I know some of it's really upper level. So if you're not quite sure where you're going with it, please reach out. Let me help you, okay? I'll talk to you guys soon.